Welcome once again to Advanced Physics for High School Students. This is Lesson 23 and it deals with wave characteristics. This lesson is packed with review information. There are a lot of vocabulary words we're going to be using in this, and I've listed them here for your reference. We'll roughly go through these in the order in which they appear. So starting in the left-hand corner, wave, pulse, periodic wave or wave train, all of these have to do with the types of disturbances that are going to be traveling in the medium. Then what follows, equilibrium position, is a particular position within the medium. And then we talk about the different kinds of waves. Transverse waves, which have crests and troughs, longitudinal waves, which have compression and rarefactions, and then types of longitudinal waves that we'll be dealing with, and transverse waves as well. Plane waves, circular waves, and spherical waves. Then we begin to talk about details of how the wave moves. So we'll talk about the wave travel direction, in other words, which way does the disturbance move, and the medium vibration direction, because the difference between transverse and longitudinal waves has to do with the relative motions of the wave travel and the medium vibration. We'll talk about parts of waves, including wavelength, which is a spatial characteristic, and period and frequency, which are time characteristics. And those things are related to each other through the wave equation. The speed of the wave is equal to the wavelength times the frequency. Then we'll begin to talk about the behaviors of waves when they get to various points. So we'll talk about reflection from fixed ends or hard boundaries and reflections from free ends or soft boundaries. And we'll talk about it in one dimension and do some simulations showing what happens with the wave when reflection occurs. And this will apply to sound, it will apply to optics, it will apply to slinkies, it applies to any kind of wave. So we're going to be talking about the different parts of the reflected wave, the incident wave, and we'll write something down called the law of reflection. And we'll label a reflection diagram, a ray diagram, showing the angles of incidence and angle of reflection. Then parts of that diagram will include the boundary and the normal to the boundary. Finally, we'll wrap this session up with a discussion of interference and the principle of superposition, which says that the amplitudes of the waves overlapping in space will add together. We'll discuss constructive and destructive interference, and then we will look at a special kind of superposition of incident and reflected waves called standing waves, and they have parts that are known as nodes and antinodes. So, fasten your seatbelt. This is a long lesson. We'll get through it as best we can. Hopefully, a lot of this will be review, but it's important as we move forward in dealing with waves. So the first thing we want to do is to demonstrate some waves. And to do that, I have a simulation that I'm going to play. You can actually play with this. What I have here is a medium, which is like a spring of some sort, or a string, or a rope, showing different beads that are colored. If I have this long thing, maybe it's something lying on the floor, and I give it a shake, then what's going to happen is I will generate a pulse. That pulse is a disturbance that travels along the medium. The medium is this string here along which that disturbance travels. There is a source of the pulse, which is a vibration over on the left side. I'll shake it again here. And that vibration travels away from the place where the disturbance occurred through the medium. The medium is one-dimensional in this case, but it doesn't have to be. It can be two-dimensional, it can be three-dimensional. Whether it's 1, 2, or 3 dimensions, then the parts of the waves are going to be the same. We're going to study it in 1 dimension. We'll extend that to 2 dimensions when we get into optics, represent it in 2 dimensions when we get to sound, but it's actually 3 dimensions when we're dealing with sound. Now I want to take this thing and I want to shake it up and down in a regular way. So I'm going to let this thing oscillate. Oscillate and vibrate mean the same thing. And when I do, I get a train of waves. And this is a periodic wave. And you can see that it looks like a sine wave or a cosine wave depending on when you happen to pause it. So if I take a snapshot of it like there, then I have frozen it in time, and I'm looking at the spatial features of this. This happens to be a transverse wave. The reason it's called a transverse wave is that the direction of the vibration is up and down, vertical in this diagram, whereas the direction that the wave travels is horizontal, and those two things are perpendicular to each other. So what we want to do is we want to label the different parts of this transverse wave, and then we want to look at some longitudinal waves as well. Here I have a frozen diagram of this wave. I want to label these parts of this transverse wave. It's called a transverse wave because there are a couple of things that are perpendicular to each other. There's the direction of vibration. In this diagram, that direction is up and down. But then there's the direction that the disturbance travels. Those two directions are perpendicular to each other. So we define a transverse wave as a wave in which the direction of the vibration of the medium is perpendicular to the direction that the wave travels. Whenever that happens, we say we have a transverse wave. Now, what are the different parts? We'll start with this dotted line that's in the middle of the wave. If there were no vibration at all, the medium, the spring or the string or whatever it is that's vibrating that the wave is going to travel on, would be at rest on this dotted line. That's the place where there is equilibrium. There are no unbalanced forces acting on the medium, and so we call that position equilibrium position. If you wanted to, you could think of this as, say, an XY axis with the origin at the place where the vibration is occurring. And so at the left end of the spring, I've labeled the origin of this coordinate system. The x-axis represents the equilibrium position, and the medium, the string or the spring, is extending along the positive x-axis. And I have a positive side of this y-axis, which is above the x-axis, and I have a negative side of this y-axis, which is below the x-axis. Now in this snapshot of the wave, there are some parts of the wave that are above the equilibrium position on the positive side of the y-axis, and we call those parts the crests. I'm going to label one crest. And then there's a part that's below the equilibrium position, and we call those parts the trough of the wave. There are some important distances in this particular wave. There is a distance that is along parallel to the x-axis. You can see that the wave repeats. This is a periodic wave, and so we'll talk about the distance of one complete cycle of the wave. First of all, let me label a complete cycle. So there's one complete cycle of the wave, and the distance along the x-axis from the beginning of a crest to the beginning of the crest of the next adjacent wave we call the wavelength. So it's this distance right here. From here to here along the wave is called the wavelength. And the symbol that's used for wavelength is the Greek letter lambda. But that's not the only place that the wavelength occurs. I've drawn it from the beginning of one crest to the beginning of the next adjacent crest. But I could have gone from the top of one crest to the top of the next crest, or the bottom of a trough to the bottom of the next trough. Basically, if you want to think about this one complete cycle in terms of particular phases, you could say a phase begins at the equilibrium position and then goes up at the top of the first crest there. Then that phase would be equal to 90 degrees, or pi over 2. When you get down to the halfway point, half a wavelength, where the wave, this is a sine curve in this particular case, if I look at it from the beginning of that crest there, then I'm at 180 degrees. And the phase there would be equal to pi, or 180 degrees. Pi radians, or 180 degrees. Then at the bottom of the trough, you get 270 degrees. And then at the end of the wave, you've completed one cycle, and that's 360 degrees, or 2 pi radians. It doesn't matter if you start at 0 and go to 360, that's one wavelength, or if you start at 90 degrees and go to 90 plus 360 degrees, in other words, the top of the next crest. All of those lengths along the axis of the equilibrium position, the x-axis in this case, are considered one wavelength. Now let's look at distances along the y-axis. you can see that for this undamped wave, in other words, there's no friction involved. When we say that the damping is 0, then that means that there's no friction involved. These buttons are adjustable. Then there's a certain distance above the equilibrium position that all the crests come up to. That's along here. And there's a certain distance below the equilibrium position that all the maximum points of the troughs come to. And that's along down here. We have a name for that distance, and that name is called the amplitude. You can indicate it either on the axis, so I have an amplitude over here, or an amplitude down here, or you could consider it from the equilibrium position to the top of a crest or to a bottom of a trough. And I've indicated those along here. So we've got several parts. We have the equilibrium position, we have the crest, we have the trough, we have the wavelength, we've got the amplitude, we've talked about the direction of travel and the direction of vibration, we've talked about the different phases of the wave, 0 to pi, 2 pi for a complete cycle. Those are parts of transverse waves. Longitudinal waves have analogous parts. Some of them are easier to draw than others. And now here is a sketch of a slinky which is being vibrated along the same direction as the springs are being coiled back and forth. So I'm going to indicate that on this diagram. You can imagine that I've grasped the left edge of this spring and I'm shaking it back and forth parallel to the horizon, so the horizontal. But that's also the direction that the disturbances are traveling. They're traveling towards the right here. And whenever you have this sort of wave where the disturbance travels in a direction that's parallel to the direction of the vibration, then we say that this is longitudinal because the direction of travel is along the same direction of the vibration. Along longitudinal. Get it? Long is in both words. We have names for the different parts of the longitudinal wave. The part where there is a tightening of the spring or a high pressure region in the case of, say, a sound wave, we call those parts compressions. And there are 4 compressions labeled here. There's one here, 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 and there. And then there's a place where the medium is more stretched out. And we call those places rarefactions. And there are 1, 2, 3, 4 of those in this diagram as well. And they're located here, 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 and here. The distance along the direction of travel, in which there's one complete compression and one complete rarefaction, is a wavelength of a longitudinal wave. You might say, what about equilibrium position? And what about amplitude for a longitudinal wave? Those things are difficult to sketch. But I have a simulation. So in this illustration, we have a woman who is listening to a loudspeaker, and the loudspeaker is producing a spherical longitudinal wave. Now I'm going to let this thing play. Where the woman is, there is no disturbance yet. Where the loudspeaker is, you can see the beginning of a disturbance, and that disturbance is going to travel towards the woman. Now the disturbance is reaching the woman's ear and passing along. And what I want to illustrate is that close to the loudspeaker, you see that there are strong waves, and those would represent large amplitude. But what happens is as the wave spreads out, the energy that it carries is being dissipated over a larger and larger area. And so the amplitude actually decreases. And you see that illustrated with small amplitude waves on the far side of this individual. So now let's label that. Let's freeze this action and let's see what that looks like. So now I have a man here instead of a woman, but what I want you to see is that there are different parts of these longitudinal waves. You could think of the compressions as the light part of the wave. So here would be a compression, here would be a compression, here would be a compression. I'm kind of making a hash of this, but you get the idea. And then the rarefactions are the dark parts, the shadow. So here's a rarefaction, and here's a rarefaction, and the wave is traveling toward the listener here. But as the wave gets more and more spread out, the amplitude of that wave gets smaller and smaller. And the way that's represented here is with the shading. So let me label the compressions and the rarefactions. A wavelength would be the distance in space between similar phases of adjacent waves. So maybe from the maximum point of one compression to the maximum point of the next compression. So I've labeled a wavelength down here kind of at the bottom of the diagram. And now let's look at the large amplitude waves that are close to the loudspeaker. And then far away from the loudspeaker, the amplitude of the waves gets smaller and smaller. The energy carried by the wave gets spread out. That's the reason when you are far from a source of sound that it sounds soft to you. But the closer and closer you get to the sound, the louder and louder it gets. Loudness is related to the amplitude of the wave. We'll see later on that frequency is related to the pitch of the sound.